two situations when we undertake research. We know the population standard deviation, and we know the mean of the population. If we know both of them, we can take a sample from the population and estimate whether the sample hypothesized mean equals the population mean. For example, the sample's hypothesized mean could be x bar and population mean is mu. We divide the difference by population standard deviation. The resulting value is an Z value where we can look up on the Z score table. If you want to place confidence in the sample mean lies within the population mean, then we have to make an estimate with 95% confidence. For that confidence level, the z-score value is between minus 1.64 and plus 1.64. If the standardized difference falls within that range, then we can say that the sample mean estimate is within the sample mean estimates represents the population mean, and we are 95% confident because that estimated value lies within minus 9, minus 1.64 and plus 1.64. And because x bar equals mu, we accept the null hypothesis because the current situation prevails. If they don't equal, if the two doesn't equal, then we reject null hypothesis because the current situation does not prevail. The second situation is we don't know the population standard deviation, but we know the population mean. If the study doesn't know the population mean, the study can find the population mean by looking at the sample and then coming up with a mean value and consider that as the population mean. Then in the research, we can hypothesize a mean value to test out whether the hypothesized mean value is equal to the population mean. We take the difference between the two means and standardize it. Because we are taking the sample standard deviation rather than population standard deviation, we adjust the sample standard deviation by dividing by square root of n. The standardized value, the standardized difference that we obtain is referred to not z-values table but the t-score or t-value table. Unlike z-value table, t-value table is constructed using sample sizes. If I show you the table, it has the significance value, that is 1 minus confidence interval 0.05 for 95% confidence level and 0.025 or 0.01 for 99% confidence level, 0.01 significance level. If the sample size is greater than 100, then the confidence interval is between minus 1.96 and plus 1.96. When we look at the t-value table, it gives us the degree of freedom, which means sample size minus 1. So 100 observations means 100 minus 1, more than 100 observations means that sample size minus 1. If the standardized value that we have computed is within the range of minus 1.96 and plus 1.96, then we accept the null hypothesis to say that hypothesized value, hypothesized mean equals the population mean. Accept the current norm. If they are not equal, then we reject the null hypothesis. If I show you the z-value table, it looks like this with the z-score value and larger portion and smaller portion. Larger portion referring to the confidence interval, smaller portion referring to the significance level. So if you are looking for 95% confidence level, we look for larger portion of 0.95, and we can see it is 1.65, larger portion of 0.95053. On the other hand, if I show you the t-value tables, you see here the first column is degree of freedom, and then two-tailed test and one-tailed test. So if the test is done thinking that any significance can be on either side, the confidence interval is on both sides equally spread, then we use the two-tailed test. And for sample size greater than 100, for the two-tailed test, it is 1.96. On the z-value table, we took 1 point. The most realistic situation is where we don't know the population standard deviation. We know the population mean, or we can find out the population mean for hypothesis testing. For us to use the means for hypothesis testing, we have to ask the question whether the sample is normally distributed. What we mean by that is, because one sample is just one representation of the population, we need to take so many samples of the population to find out whether the means of the population are normally distributed. The population doesn't have to be normally distributed, but they are the means that has to be normally distributed about the population. So that is done by taking numerous number of samples and then plotting the means of so many samples to find out whether it is normally distributed. If means of samples from the population are normally distributed, then we say that the population is normally distributed. And then we can test whether the sample mean that we have taken equals the population mean. But sample mean, when we equate to population mean, we have to acknowledge it is a sample, and therefore it may not fully represent the population. That means sample mean can have an error. So the sample mean error can arise from three sources. One is the sample size. Smaller sample sizes is less representative of the population, and smaller samples can increase the error of the mean of the sample in relation to the population. When the population is diverse, taking a sample from a diverse population compared to a homogeneous population makes the sample mean to be erroneous because it may not represent the required diversity. Thirdly, the sampling plan. The sampling plan should follow the population characteristics to be representative of the population in the sample. But an inappropriate sampling plan can increase the error of the mean of the sample in relation to the population. This error of the mean of the sample is called the standard error of the mean. And as a result, when we talk about the population mean, using the sample mean, we have to provide a range in which we can say the population mean will lie. And that range required to express within which the population mean lies depends on the sample error. Smaller sample size, higher population diversity, inappropriate sampling plans increases the error of the sample mean or the standard error of the mean, and expressing the population mean within which the estimated sample mean can lie requires a wider range, a wider confidence interval, so that we can say that the sample mean lies within that wider range or the wider confidence interval to represent the population mean.